is it right to place ferrite beads into power rails, or it's something bad to do? And that's what we are
Right.
going to talk about today.
So when it comes to ferrites, you want to ask the question, what is the problem they're solving? And given that problem, how do I engineer it? The problem is part of power integrity. It's about the power delivery network. And so I thought I would I'll show this slide here. I thought I would introduce a really simple circuit diagram of the power distribution network that illustrates many of the, not all, but many of the problems that can arise. And that is always the first starting place to think about, how do I want to, what is the best design practice? How do I want to engineer the interconnects? What problem am I trying to fix? And so here is an illustration of the schematic of a power distribution network. From over here on the far left is the voltage regulator module. This is where the DC voltage is coming from. And then over on the far right is one of the actual devices, that a chip that is being powered by that VRM and is then doing something. And this, I think, illustrates the root cause of a number of the problems. And the key principle in not just power integrity, but all electrical design, optimized design, is that there are usually more than one problems that with different root causes. And so you have to identify, what is the problem we're trying to fix, and what is its root cause, and fix it at the root cause. And I think we had a discussion some time ago about decoupling capacitors and how we use them and what their roles. And we identified a specific problem that we're trying to fix with decoupling capacitors. And just to illustrate that, this is I've got the schematic set up to illustrate a device over here. Here's some IOs they're going to switch. And when they switch, they are going to drive current. They're going to drive current into their outputs. And that current comes from the power distribution network. And the problem that's generated, if we don't pay attention to it and fix it ahead of time, is that from the voltage regulator module to the pads on the chip here, where the IOs are switching, there is inductance in that path from the physical nature of the interconnects, the power distribution network. And when I have a large DIDT, when I have a lot of,
So to explain, what does it mean there is inductance? What is it going to do with the power delivery?
In fact, just yesterday, we talked about inductance and what it is, the physical nature of it. And inductance literally is related to how efficient the geometry of the conductors are at generating rings of magnetic field lines per amp of current. So it's about you get current going through a wire, you get rings of field lines, magnetic field lines going around it, and the more field lines I get per amp of current, the more inductance. And the problem is, when the field lines change, the so what of inductance is, when those field lines change, the number of field lines around a wire changes, they induce a voltage. And I think that's Faraday's law. And that is the fundamental problem of why we worry about inductors whenever we have a changing current. And then changing current generates a voltage, and that voltage is switchiness. That's why, the IV property of an inductor is the voltage across an inductor is LDI/dt. And can I draw on here? Let's see, maybe I can do that. So, oops, get rid of that. And let me get rid of this thing here. So the inductance, the voltage across an inductor is LDI/dt. That's the kind of defining relationship about voltage and current of an inductor. And that is the fundamental problem, that when I have a changing current, switching current going through the inductor, I get a voltage generated. And so here is my switching current. Here's the IO that's switching, and all that current comes ultimately from the VRM, and it's going to go through all the inductance and all the wires there. And when I increase my current, when the current's going this way through the path, then that I'm going to have a voltage across each inductor. Here's the plus side, here's the minus side, here's the plus side, here's the minus side. I've got all this di dt going through these inductors. I get a voltage drop. Well, this guy here, he fixes the voltage on that power rail. I don't know, maybe it's 5-volt power rail. He fixes that voltage. And so this voltage is fixed. This voltage, when I get current flowing this way, increasing, this voltage drops, and this voltage drops, and this voltage here drops. And that means that when I have I/O switch, all that di dt through all that inductance gives me a voltage drop on the power rail, and everybody else on that power rail sees it. And I'm going to show you an example of it. I have it set up. We're going to use that as a source of noise. And the way you fix that, so that's the problem that we want to fix. We call it sometimes power rail droop, or we call it, it's basically that LDIDT, voltage noise on the power rail. And if we're not careful, that can be huge. And the more current that we switch, the faster, the shorter the rise time, the larger the amount of voltage drop that we see there. That's one of the power integrity problems. And I think in one of our previous videos, we talked about how we fix that problem. We do that by moving the VRM as close to the device as possible to reduce that inductance. And we said, hey, you can't do that in practice. And so we use a surrogate VRM. We use a temporary VRM. That's the capacitor, the decoupling capacitor. That stores charge for a short period of time, just during that rising edge or falling edge, just during that DIDT, so that we can place those capacitors. Well, here's the capacitor. We can place it really close to the chip, and then all we have to do is worry about the inductance from the pads on the chip to the decoupling capacitor, and that's the only inductance that contributes to the voltage droop. And that's why we say, hey, if you're going to use capacitors, it's not about their capacitance as much as it is about their inductance. Bring them close to the device. So that's one of the problems, the switching noise due to I/O current and DIDT through inductors. And the solution to that root cause problem is use decoupling capacitors to act as VRMs, local VRMs, in close proximity to the chip only during the edges when I have the DIDT. And that will dramatically reduce the inductance, dramatically reduce the switching noise. So that's problem one. So ferrites play zero role in that problem.
Okay, we will go back to ferrites. I just would like to point out, some people may not, or I would like to point out that these losses, because of the inductance, can be actually quite high. So it means, for example, if we should have 3.3 volt power voltage, then the drop can be, for very short time, drop can be also number of voltages, like 1, 2, 3 voltages, and that's like really bad. It really depends on how high current we would like to drive. So it's not like only a couple of millivolts or 100 of millivolts. It can be in volts. That's what I wanted to point out.
In fact, in the demo I'm going to show you, you're absolutely right. I've got a 5-volt rail, and we're going to have 3-volt drop on it. It's going to go down 2 volts. Huge. If you don't pay attention to the problem, if you just design the interconnects for connectivity, this kind of problem can completely swamp your system.
Mm-hmm. Okay, so now let's go back to bead. So what do you think?
Yeah. Right.
Where do they come from?
Why? So clearly in this problem, there is no role for ferrite beads. Ferrite beads don't do anything to solve this problem, because it's all about the current draw from the device and the DIDT through the inductors. Okay, so second problem.
Maybe we should explain what ferrite bead is first.
Yeah, so when we talk about ferrite, a ferrite is the name refers to the type of material that's inside. It is literally an inductor, but it's a special kind of inductor that is, it's either literally a little wire coil, or it is a structure that is patterned to be a coil of some sort. And there are generally a number of families of inductors. That one family of inductors is called a power inductor, which is designed to be low loss and allow high current passing through it. And they are used in fact, you can see it in this picture here for the voltage regulator module. Here's this whopping big inductor. It's a power inductor, and it's designed to have relatively high inductance to allow high current pass through it and still be effective, and relatively low loss. So they're called power inductors for power applications. Another type of inductor is designed for filtering when you don't have a lot of current, and that's where ferrites are used. They typically have one of the big differences is in a power inductor, the DC resistance is measured in the milliohms, 1, 10, 20 milliohms, and you want it low because you're going to pump a lot of current through it. You don't want a large IR drop through it. That's power inductor. For a ferrite, the DC resistance is usually measured in half an ohm, 1 ohm, 2 ohms. So it's a 1 or 2 orders of magnitude higher series resistance. You're not using a ferrite for high current. You're really using it for filtering. And many times when you filter, especially we're going to see here, we're going to use it as a low pass filter. And whenever you have inductor and capacitor, the first thing that comes to mind is resonance. We've built an LC tank circuit, and the way you minimize, and in the power distribution network, whenever you think resonance in power distribution, you want to shudder a little bit, and you want to be a little bit afraid. Oh no, because a resonance means we're going to have a high impedance usually, and that means any current passing through that high impedance at that frequency potentially can generate a lot of noise. And so we don't want resonances in the power distribution. And when we use a ferrite to filter, or I should say when we use an inductor to filter, we're going to have an inductor and a capacitor. We don't want a high Q, and that's where the resistance of the ferrite helps, because it will help damp out that high Q. So it's actually a feature rather than a problem when it comes to filtering. So a ferrite is basically an inductor, and it's generally used for lower currents because of the high series resistance associated with it. So now we can talk about what's the problem it's solving. So here's a second problem. Here I'm going to use the same illustration here of my power distribution network. And now suppose that, I've got my devices switching and they're drawing current, and here's my voltage regulator module here, and I've got these other devices that are switching and drawing current, or I've got my voltage regulator module, my switch mode power supply, and it is generating its volt. It's a buck converter, it could be a buck or a boost, but it's basically taking a DC voltage in and giving us a DC voltage out. And to do that, it is switching voltages. And when it switches, that means it's going to have some high frequency noise on it. And that's where its output, we generally have, that's what the role this is playing, we generally have an LC filter. It's a 2-pole filter to filter out that switching noise. That's fundamentally what it's doing. If we didn't have the LC on the output, we'd have a lot. It would be basically a pulse width modulated voltage coming out. The inductor and the capacitors filters it out. But depending on where the pole frequency is, depending on how much switching we have and some other things, we're going to have some noise. And so when we look at the voltage rail with a switch mode power supply, especially when we have a current load, DC current load, we're going to see noise on it just because of the nature of the switch mode power supply. I did a webinar with my buddies at Tele and LaCroix. I can't remember if it was this year or last year, where we actually looked at that. We looked at the switching noise on a switch mode power supply as we changed the DC load. And you see on some of them, because of the nature of the regulation, as we switch, as we increase the current load, just DC current load, you see more and more switching noise. And so that's one source of problem. Another source of problem is we have other devices that are on the line. They're switching. They're going to pollute that power distribution rail. So even though we're protecting the I/O here and we're adding decoupling capacitors, we don't get much noise injected back. We're going to get some. That means that anybody else that's tied to that power rail, that's distributed in the plane of the board or the system of the board, anybody else is going to see that pollution noise on that power rail. It's not that device's fault. It's the fault of everybody else, including the VRM. That's where the noise came from. But when we have a device that is particularly sensitive to voltage noise on the power rail, like an analog to digital converter that has a reference voltage in it, or a DAC, or a PLL that has some of its the VCO or the oscillator in it. If the voltage, if the noise on the power rail moves a little bit, that induces jitter in the clock in the PLL. I did a webinar with Kelvin LaCroix. Again, I can't remember. It was earlier this year. Yeah, I think it was early this year, about power rail noise induced jitter. And we showed a couple of different oscillators that, depending on the type of oscillator, you get noise on that power rail, and that directly drives jitter in the clock. So you get some devices, not every device, but some devices are really sensitive to the power rail noise. Generally, it is analog devices, because the digital ones, they're pretty robust. You know, that's where the noise margin comes in. But the analog devices, really sensitive. And that's why if you look at microcontrollers or devices that are mixed signal, that have digital parts and analog parts, they will have a VDD, that power rail for the digital components, and they'll have an VCC or a VDD that is power for the analog, powering the analog part of that chip, because they are so sensitive to noise. And so here is a separate problem, a different problem we talked about. I've got a device here, and I'm going to use this device to illustrate it. I'm going to see if I can clean up the marks that I put on here from before. So I've got this very sensitive analog device that is connected on the power rail over here, and it wants to see really constant voltage, really low noise. And so I want this voltage here that's powering my device, I want that to be low noise. And I'm not going to draw a lot of current. Most analog components, they draw in the tens of milliamp kind of range. And so this is small. The current that's drawing is pretty small. But I've got all this noise on the power rail over here, and I want to see less noise over here. And that noise is, I get the switching frequency, I get the clock noise from IOs that are switching, and so it's a lot of high frequency stuff. I just want a DC signal over here where my device is. And so one of the most common ways, I mean, we can fix that problem in a lot of ways. One way is, you know what, I'm going to give my analog device its own power supply. And I don't want to use a I don't want to use a switch mode power supply, because that has inherent noise. I want to use a linear supply. So one solution is, you know what, I'm going to give this guy its own linear supply, and this will be, call it 3.3 volts. I'm going to send 5 volts in. Here's ground. I'm going to use an LDO. It's a low dropout regulator. And even if I have noise over here on the 5-volt rail going through the LDO, if it's a good LDO and it's got good feedback, I won't see much of that noise coming through. There's a power supply rejection ratio that tells us, that characterizes the LDO, how much input noise transmits output noise. It's a great way of supplying power to my analog devices that are really sensitive. But it means I got to throw a separate regulator on there, and I got to make sure the input voltage is large enough so any voltage noise on it is still above the minimum voltage I need on the input of the power supply to give me my constant voltage coming out. But perfectly fine way of doing it. And it's, you know, it's a lot of board designs. Another way of filtering out that noise is literally adding a filter. And that's where ferrites come in. if I have the specific application of a device that's very sensitive to noise, an analog device that's not drawing a lot of current, then I want to add a filter from all this noise on my board into the device here, so I have a low pass filter. And I want to design a filter. So here's my transfer function from the power over here on the board level power. There's the board level power to where it is on the die itself, on the die. This is for the analog device. I want a low pass filter. That means at low frequency in DC, I want it all to come through, but I want it to drop off as I go up in frequency. And you know, we describe it in terms of the pole frequency where it starts dropping off, and I want that pole frequency to be as low as I can, so that any noise that exists over here gets filtered out, doesn't get through. And so I want to add a filter between that noisy power rail on the board and the pads on the die over here that are so sensitive to that voltage noise. And I'm going to do that by using an LC filter. And here's what that filter looks like. And I got it over here. I'm going to redraw it down here. I'm going to have an inductor and a capacitor. And if I have this circuit and I look at the transfer function from the input to the output, I'm going to see this response. This is going to be two-pole response. It'll drop off at minus 40 dB per decade of frequency. And high frequency noise that's way over here, it won't get through that filter. And that is how we're going to use ferrites. And this inductor here is going to be, we call it a ferrite, but it's just named for the material that's inside of it. It's literally an inductor that's filled with the ferrite material. And if I wanted to, I want that pole frequency here, I want that to be as low as I can engineer. At a minimum, it's got to be, like an order of magnitude lower than the switching frequency for the switch mode power supply here. It's got to be an order of magnitude lower than any clock frequency or any other source of anybody else that's periodically switching. And so knowing what is the highest frequency, the pole frequency I can go with, it's about knowing what else is going on in my system. And switch mode power supplies, depending on which one you have, maybe it's 10 kilohertz, 100 kilohertz. Some of the high-end ones are megahertz even. And so I want a filter that, maybe as a pole frequency at the highest is, maybe in the 10 kilohertz kind of frequency range. If I get one at 1 hertz, that's even better, because that means anything above 1 hertz, I'm going to filter out. So, yeah.
Now I have a tricky question. Just a couple of minutes ago, we were talking about we don't want to have inductors in power rail. And now we are saying inductor in power rail is going to help us.
Right.
So why
completely
is it?
Different
I know
problem.
why is it, but
completely different. Right. Because when we have, typically, if we look at the behavior of analog devices, their current draw is more constant. We don't have a lot of IOs that are switching. If we have a high current output that is going to switch for the analog component, generally it's going to use a different power rail than that sensitive analog one for exactly that reason. And so and that's why we only want to use a ferrite on a device that's not going to draw a lot of current, because it has so much DC resistance in it that if it draws current, we're going to get a DC voltage drop. And who wants that on their power rail? And so if you and so it's specifically to fix the problem of we've got a noisy rail and we want to filter that from the very sensitive analog device.
So important is low current. We can use it in low current power rails.
Right, right. And the last thing that we want to do is use it in a low current device that has high DIDT. If it's going to be switching, then generally we don't care about that low constant voltage and low noise. We care about the switching noise, and it's all about that decoupling capacitor with it with low mounting inductance to the component. We still want to use low mounting inductance because any inductance in this path, if we built a filter on this path and this was a low impedance, then we would be sensitive to the noise and the any currents that are switching over here. And so, yeah, we always want to have low mounting inductance for the capacitor that's in close proximity, but that's to fix the switching noise generated by itself. It's self-induced switching noise. The role of the ferrite is to fix the problem related to everybody else causing the noise. It's the, I hesitate to say the mutual noise, but I call it the pollution that exists on the power rail. That's the problem that we want to fix. And so if your device has a noise margin of tolerance on the order of 5%, 10% of the voltage noise on the power rail, generally you don't need a filter, because the noise on the pollution on the power rail should be less than 5 to 10% if you do right. But there are a lot of analyses that 5% of noise on the power rail is too much. That will contribute to, if you get a 16-bit ADC, there's a limit to how much the chip will filter the power rail. You need to provide low noise DC voltage. A 24-bit, if you're doing audio applications, getting that voltage noise on the power rail reduced is really important. If you've got a PLL, getting the voltage noise on the power rail, you want it less than 1%. And it's too big a burden to tax the entire power rail to be less than 1%. I don't think you could afford that solution. But we can either use a local, a linear regulator of some sort, or filter with the ferrite. Mm-hmm. And that's where the ferrite solution comes in.
So let's have a look on your example, because you don't have much time.
Yeah, let's take a look at the example. So I'm going to show you this board. This is a little better close-up of it. This is a test board that, again, this is an example we use in our PCB class. We illustrate what's a ferrite, how do you use it, and how do you integrate it into a board. And so this is a little test board to illustrate filtering of a power rail. So this side of the test board are going to be the inputs. This is where the noise on the power rail is going to be. And then this side is on the other end, looking at how effective is the filter. And I have an example here, just a straight through. And you can see the, whatever noise we have on this side, we're going to see it on this side, right? And then I have, what if you just put an inductor there? So we just add an inductor from one side to the other. And again, remember, this side is going to be connected to our analog power rail input. It's not going to draw a lot of current. It's going to be kind of constant there, relatively high impedance. And so we're going to look at what is that voltage that we see on this side when we just have an inductor in here, right? And, we always have some capacitance over here. And when we have noise over here, we're going to have an inductor and a little capacitor over here. You can expect to see, we're going to see some ringing noise. And then the third example is, here is the schematic of this. So here's my inductor. The black term here is the inductor. It goes over to this side to where the capacitor is, and then the other side of the capacitor, this goes into the output pin over here. And so this is the configuration that is a filter, that we have noise over on this side, and here's our LC filter over here, and we're going to see if the frequency components of the noise here are well above this LC or this pole frequency, we're not going to see much noise over here. So that's the setup. And now I'm going to take you in the lab and I'm going to show you what we're going to look at. Okay, any questions about that setup?
No, I understand.
Okay, so I'm going to take you in the lab. So here we are in the lab, and now I'm going to, and I apologize, I didn't have time to set up my scope directly into my computer, and so I've got a kludge here so we can see the scope. So I'm going to move over to the lab here, and so I'm over here in the lab. Here's me. Hi there, and here's our circuit. And so to generate a source of noise, I'm going to do that experiment we talked about. I've got some voltage coming in here. That is the power rail, 5-volt power rail over here. It's just coming from a small regulator, and then I've got a transistor here to emulate what the an output IO is going to do. It's going to switch current, and it's going to do it pretty fast. And so I have a little signal, a green wire here, is coming from a little microcontroller, and it's going to generate a pulse to turn the transistor on. So I'm going to see edges from that transistor. We're going to look at that edge. And so that's going to be my noise source. That's going to pollute the power rail on my board. And then I'm going to look on the other side of my filter here. I've got, let me see if we can get a little closer view here.
But there is the, yeah, okay.
Yeah, so we're gonna look on the other side, and we're gonna look at how much comes through if I have a straight pass, how much comes through if I just put an inductor there, and how much comes through if I put an LC filter. How well are we able to filter that noise? And so let me just start out, and I'm gonna zoom out a little bit. Maybe it would help. I'll show you the circuit here of what I have connected. Let me go back to the slide here, and here's the circuit.
Yeah, okay, that's 10 ohm resistor. That's what I thought. There is big resistor.
Well, that's just a sense resistor. This is the load. Was the whole circuit here?
Yeah,
but it's the transistor that's turning on suddenly, that's drawn a lot of current, and I'm using this as just the sense in order to control the current, and we're going to look at that current flowing through there. Okay. So we're going to look at the voltage across that 10 ohm resistor, and we'll see that, and we'll look at the voltage on the power rail itself. And so we're going to send a signal going in. It's going to turn that gate on, and that's going to generate pollution noise on the power rail. Okay. And then we're going to use that as our source to send it through the filter. And
the filter is where exactly?
That's on the other side here. Okay. So this is the power rail, and we're going to put the filter over here. Okay, and we will measure behind the filter. Yeah, okay. On the other side of the filter, how effective that filter is. Okay. So let's go back and we'll look at. Here's the filter. So here's the power rail. In fact, literally, here's the ground. Here's the power rail. We're going to pollute it with this guy, and then we're going to send those signals through all the way through the inductor and through the LC filter. I understand. So let me grab my scope. Here's the scope image here. Okay, so I've slowed it down a little bit. In fact, I'm going to slow it down a little bit more so we can actually see the pulses that are coming through. And so we have, it's not very long. Every maybe like 25 milliseconds, I'm sending another pulse through, and we're going to zoom. So this is the current going through the transistor that is drawing the large DIDT through the inductance of the power rail, and that's going to generate the voltage noise. So if we zoom in on that edge, so we're just going to look at, this is the current turning on, and it's pretty fast. I've got 20 nanoseconds of division here on the scope, and so it's turning on in about 20 nanoseconds. That's kind of the turn on time for the transistor, and it's literally limited by there's so much power rail noise. I am literally turning the transistor off because the voltage drop is so much. That's why it's 20 nanoseconds, and we're looking at I'm going to turn this one off for a second. So the red trace here is the voltage I'm measuring on the power rail. That is the pollution noise. And let's see, the scales, let me show you the scale for that. And so here is 5 volts for the power rail. It's 5 volt constant voltage. And now when I turn on the transistor, that voltage drops 4 volts, 3 volts. It drops below 3 volts. It's about, so that's a 2 volt drop, 2.5 volt drop out of 5 volts. Huge drop. And it's literally limited because I reached the saturation of the transistor and it can't drop anymore. And that's why it turns on so slowly. So it's a pretty large amount of noise that is on the power rail. And we're going to keep that up so that you can compare the noise that's present with the signal that comes across. And the first thing we're going to look at, and I'm going to turn on the blue channel here, we're going to look at the through path, and we should see exactly the same noise. So let's turn that one on, and there it is. And we're on the same scale, and you can see it's almost exactly the same amount of noise. That we've got the same 2 volts, more than 2 volt drop there, because it's just a pass-through. And so I'm doing something that I'm setting a bad example. I'm doing something that I tell my students never to do. When you measure a signal with a rise time that's less than, my rule of thumb is about maybe a microsecond, or at the very shortest, 100 nanoseconds, a tenth of a microsecond. If you measure a signal that's shorter than a tenth of a microsecond, be very, very careful about the loops that you generate in how you probe. And I always recommend use the little spring tips on the scope probes to minimize the loop inductance. That minimizes the signal distortion and minimizes the probe-to-probe crosstalk. And our rise time here, it's 20 nanoseconds. It's well in that high-speed regime. I would, if I saw a student of mine doing what I'm doing here, I would have gone by, I would have slapped their wrist and told them, don't do that. But I had to put this together really quickly, and I couldn't find enough of the spring tip, so I'm using this method. So this is my caveat here: don't do what I'm doing. And that's partly why the signal, you know, has some ringing on it, because I've got these long loops here, and I've got a little bit of probe crosstalk, but it's illustrating the principle that I want to show. So we're looking at the blue guy, and we're looking at the through, and it's exactly the same thing. Now let's switch, and I'm going to look at the inductor. So what if we just put a ferrite in there? And, you know, everybody says, oh yeah, ferrites are good. Let's just put a ferrite in that path. And so there's always capacitance everywhere, small amounts in the picofarad, tens of picofarad kind of amount on die or in the package lead. And so in addition to having that ferrite that we physically put on the board, we're going to have a little bit of input capacitance on the silicon itself. And when we do that, I'm going to slow this down. When we do that, that's the voltage that would appear on the analog input pin, the A VDD or VCC. And I haven't changed the scale. We're at 1 volt per division. We've got, you know, 2 volt peak to peak ringing noise on the output that is the power rail of the IC, and it's not drawing a lot of current, and so it's relatively high Q, and so we're going to see ringing like that. And you know, any more current draw will damp it out a little bit, but it's hard to know how much there is. We run the risk, if all we do is put a ferrite there, of getting a lot of ringing. And it's relatively high frequency. Let's see, we can measure it off the front screen here. It's about 1 cycle per division. We're at 100 nanoseconds a division. So that's like 10 kilohertz. No, I'm sorry, 10 megahertz is the frequency. And so, you know, we get 10 megahertz noise on the power rail that is going to be translated into high frequency noise that's going to come on the analog output, or it's going to affect if it's a PL, affect the output frequency.
So we made it even worse.
We made it even, well, I'm not sure. They're both bad. Whether we have the trace that is the red trace here, where we have that large dip that didn't last for long, or we have that extended ringing, they're both a problem. And so the last thing you want to do is just throw a ferrite somewhere thinking it's going to filter things out. Instead, we design with intent. We want to engineer an LC filter. That means we need a C on the other side. And so here is the third example. I've got my LC. I'm doing it right. So this is an LC filter to filter out all that pollution noise. So let me move over and we'll look at that filter noise. And there it is on the same scale. And yeah, okay, I got some noise coming through. You know, I got, you know, my wires here. It's got a pole response. There's some other high frequency coming through, but you can see it's dramatically reduced from everything else that we've had. That's why we add a ferrite filter. It's not just the ferrite. It's the LC that we're adding to filter out the high frequency noise. And so the pollution noise we have on this power rail, it's on this side of the device, does not get to this side of the device. And that is why we have ferrites.
Thank you so much, Eric.
I wanted to plug a new master's program that we have here at University of Colorado in Boulder. It's very focused program specifically on this area of signal integrity. If anyone is interested in wanting to grow their expertise and become more valuable in the industry as an engineer with signal integrity or power integrity experience and the skill set that many companies are looking for, I invite you to check out our landing page and you can find out more information about it. We do encourage transfer students starting in the spring semester or starting in the fall semester. So there's my product placement ad for the program that we've got going. Okay. Any other questions?
No.
Okay,
I know you are
sounds
super
good.
busy. So I would ask many other questions, but I know you are super busy.
We'll
We
do it
have to
another time.
finish.
Yeah, we'll do it another time. I have lecture in a little bit, and we talked about inductance yesterday. The day before, today we're going to finish up talking about capacitors, and then we're going to talk about after their midterm next week. My students are going to learn about the first order response and second order response, and one of the examples is literally going to be how to analyze the filter response with an RLC circuit. And so this is all of this stuff we're talking about is exactly the kind of stuff that every electrical engineer should be learning in a circuits class.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEval online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.